Let's go ahead and look at another example. In this example, when we're trying to find the derivative of this function, we're really going to have to use a lot of algebra. So again, your algebra skills need to be really sharp, first of all rewriting this to begin with, and then after we take the derivative, in order to simplify it, we need those algebra skills as well. So the first thing that we need to do is some prep work. We need to rewrite this. Now remember, we want to rewrite this until we have x to some exponent. That's all we have right now. We don't have any rules about products and quotients or chain rules yet. All we have is our good old power rule. So we want to rewrite each one of these so I have an x to a power. Well, we've already looked at this one. In this particular case, we know we need to rewrite this as x to the negative 1. Now I have an x to the exponent. Here I'm going to just drag along my 3/2. This root x is the same as x to the 1/2 in the denominator, but when I flip it into the numerator, it becomes x to the negative 1/2. And here I have x to the negative 4/3. I don't need to rewrite that. It's already an x to an exponent. So now when I take my derivative, the derivative of the sum is the sum of the derivatives, so that means I can take the derivative of each piece. I bring down the exponent, and then I decrease the exponent by 1 and drag along any constants or coefficients. So bring the negative 1 down, decrease the power by 1, drag along the 3/2, bring down the negative 1/2, decrease the exponent by 1. Now the fractional exponents get a little bit tricky, but you'll get used to working with those. Plus, bring down the negative 4/3, decrease that exponent by 1 as well. Now we can't leave this answer. This is not even close to being done. I need to get rid of these exponents where I'm adding and subtracting in the exponents, and of course getting rid of negative exponents would seem like a good idea. So let's go ahead and keep rewriting, and again, do not drop this derivative notation because I have two functions running around now. I have my original function and my derivative, so I do not want to drop my derivative notation because that will show me which one is my derivative as opposed to my original function. Well, up here in this exponent, minus 1 is a minus 2, and so I can flip it down into the denominator. Over here, I have 3/2 times a negative 1/2, and I have a negative 3/4. Okay, now, negative 1/2 minus 1. You have to be careful with these. If you want to think of this as negative 1/2 minus 2/2, because of course 2/2 is the same as 1, you can see here that I get a negative 3/2. But when I flip that, I'm going to end up with that 3/2 in the denominator. Now over here, I'm going to have a negative 4/3 x, and I know this is going to be a negative, that's why I already wrote it down there. So this is going to be a negative 4/3 minus 3/3, which would be a negative 7/3 in my exponent. And that's your derivative. That's the slope of the tangent line at any point along the graph. You can check these in Maple. So let's go ahead and look to see how we check this in Maple. I don't have the whole window open here. But in order to check this in Maple, you can use the command line DIFF, or if you look over here, this looks like a derivative notation. And then in here we'd put our function. So let's go ahead and input that function that we were just working with. And you can see after you input the function that we do get the same derivative as we did when we were doing it the long way by hand. So we can take a quick snip of this and pull this into our notes to kind of remind us how we can take a derivative in Maple. So you can check a lot of your answers in Maple. Now a lot of times Maple will simplify a little bit differently, or you might simplify a little bit further. For instance, you might want to find a common denominator here, and that would be fun to do. It's going to take a while though, because it's not a very nice little denominator. The last thing that we need to talk about during this lecture is differentiability and continuity. If I have a function that's differentiable, that implies that it's a continuous function. So differentiability implies continuity. However, this does not work both ways. This is not vice versa. For instance, if we have something that is continuous, that doesn't guarantee that it's differentiable. So Differentiability implies continuity. Continuity does not necessarily describe something that's differentiable. Types of points that are not differentiable are cusps, this little needle point right here, this sharp point. This is not differentiable at this point. Where would a tangent line be? Here would be a tangent line, here would be one, here would be one. So at a cusp that doesn't work, and that also works with a sharp point. These are both continuous graphs, but they're not differentiable. And again, here I have that same problem that we're looking at. Let's go ahead and look at one more last example that kind of brings this point across very nicely. Let's go ahead and look at the graph y equal x to the 1/3, and I would like to figure out what y prime is. Now remember, this y prime notation is the notation that was introduced by Leibniz, so we haven't used this one quite yet. So y prime would say I'd bring the 1/3 down and then decrease the exponent by 1. So rewriting this, I have y prime equals 1/3 x to the -2/3. 1/3 minus 1 is a -2/3. Okay, rewriting again. This gives me 1/3 x to the 2/3. So this is a continuous function. X to the 1/3 is a continuous function. Let's go ahead and look at that graph. This is on the graph of our very first day of calculus class. So this is the graph of x to the 1/3. And I have a little bit of a problem though. This is a continuous function, but I have a problem right here. Right there. Now, what's happening here is this is a continuous function everywhere except x cannot equal 0. At x equals 0, f prime of 0 would equal 1/3 times 0, which of course is 1/0. This is undefined. This is not the original function. The derivative is undefined at this point. So you can see that continuity here did not say that I could find a derivative here. And specifically we're looking at 0. So here the derivative evaluated at 0 does not exist. So the tangent line has infinite slope at 0. And that's kind of interesting. The tangent line has infinite slope at 0. X equals 0. So again, this straight up and down line, remember that's a change in y over the change in x. There is no change in x because it's a vertical line. So I have that infinite slope. I have that vertical point. So in this case, I had a continuous function, but it was not differentiable everywhere, even though it was continuous everywhere. So kind of our big takeaway points here. On a test or a quiz, you're going to need to know how to use the limit definition of the derivative. So make sure that you know how to do that. But we're also going to be able to check a lot of those answers using our power rule now. Thank you.